Good day, welcome to this video. In this video, I'm going to be showing how to code an SPWM routine in a PIC microcontroller, specifically a PIC24 FJ64GA002. It's meant to just show the routine on how to go about coding SPWM um, generally, but this particular microcontroller does provide an avenue. Well, there is a way to simulate the results of this. So obviously the better microcontrollers to do this than this particular one. Yeah. So I'm just gonna get right into it. First I'll just show the basic schematic of what I'm talking about. So this is a full bridge inverter for MOSFETs, in-channel MOSFETs for in-channel MOSFETs, driven, and you have two MOSFETs, so these two are turned on at the same time, and these two are turned on at the same time. So basically, the whole point is to have a sine wave across the load, and to vary the how do you say to vary the PWM across a MOSFET pair over the over half of the frequency that you desire. So looking at the code, that'll make much more sense. So basically, this is the basic schematic. Obviously, if you were gonna do this in the real world, there'll be much more to it. But in terms of simulation wise and showing the code structure, this is enough. And obviously, there should be a filter here. But before I put that filter, I sort of want to just see what the signal is gonna look like. All right. So this is the code and the initialization. So first up, the first one is the pole, because remember there are two MOSFET pairs. Um, so this polarity is just to sort of tell, okay, when do we switch, at what point do, which one are we switching on right now, and which one are we zeroing out, which is going to be a zero, which is actually going to be on at this point in time. So that's what this is for. This is the polarity to indicate which one we're turning on. It'll make much more sense when you actually see the code, where the section of the code where we're switching it on and off, etc. And this particular count variable is to actually calculate the PWM values for a cycle, for a SPWM cycle. And the count max is 200, so 200 is the number of times the PWM actually changes. So basically, if you have more PWM changes, the more sinusoidal it looks after filtering. So you want this to be sort of as high as possible that your controller can do, basically as high as your controller can go. So in this case, 200 is a pretty good number. From my um little experience doing this, if you could go as low as 25 and it still work out, but 200 is a good one. And actually, this value here, the max value, number of time you actually change, it all depends on your timer interrupt, right? So I'm using a timer interrupt in this case. It all depends on the frequency that you want for your sine wave, the frequency on your output, and also depends on the timer interrupt, how often the timer triggers. Like in this case, I'm using a timer interrupt. So this is the formula that you use. So it's 0.5 multiplied by the period of the line. So that's 1 divided by the frequency. In this case, the frequency I'm going for is 50 hertz. So the T line here is going to be 1 divided by 50, which is 20 milliseconds. And you have to say that divided by, and you have to say that value divided by the T end. So in this case, from the MCC initialization, I'm using timer 1. That value is chosen to be 50 microseconds, right? So, let me see again. Yes, 50 microseconds. So, no, that's not where I want to go. Yeah. So this T int is going to be 50 times 10 to the power of minus 6. And if you do that calculation, the value you get is 200. So once again, it's 0.5 multiplied by T line, which is 1 divided by the the frequency of the sine wave you're looking to get off to your inverter, because remember you're having an inverter and the sine wave has to have a certain frequency. So I'm going for 50 hertz in this case. So this is going to be 1 divided by 50 t line, and t end is 50 microseconds in this particular example. So the answer is going to be 200, right? So this is the count max, and this is the PWM pole. So this is going to be the what we're using to track the PWM of the first pair and the second pair. Then this is the sine array, obviously 200, where we're actually storing the SPWM values, initialized all to 0.0. It's a float sine array. And there are actually two ways of doing this, right? So you can actually calculate based using the sine function. Obviously, you have to use the math library. So you use the math library and you can actually calculate on each time. So in that particular interrupt, for each PWM, you actually use the sine function to calculate the required PWM for each time. But that actually takes a lot of time. Like it takes a lot of time actually, because the sine function takes time. So it's better to actually calculate the entire sequence, the entire array, everything. First off, before you actually start to do it. So you calculate the entire array and then you store it in here. And then in the interrupt, all you're doing is just accessing the values in this array, which is a lot quicker. So basically, you can go 50 microseconds, even sometimes I think you can go 25 microseconds for this microcontroller. I haven't actually tried it. The lowest I've tried is 50 microseconds. But if you were calculating on every cycle, it will not work. It will take too long. I'll show you what I mean. So first off, so here is a for loop where you actually calculate the PWM you require for each. Let me just show what I'm talking about. So what you want on the output is this, right? Oh crap, that looks horrible. Anyway, it'll just take an eraser there. Alright. Wow, this is taking a long time. Yeah. And so, right, so this is what you're looking for on the output. And essentially what you have to do is you have to have various PWM signals. And here obviously the PWM the maximum, because your input is actually like a smooth DC, more or less like that. 400 volts thereabouts, and then you get like an RMS of 230. Obviously varying the with a lower maximum duty cycle, but your RMS you can get it to be 230 volts. Anyway, with this coming in, you sort of have to let me zoom into that. With this DC waveform coming in, you sort of have to make your MOSFETs vary throughout this, and this is a sine function, right? So the sine at this particular point, right? The sine here is basically, this is sine 0.5 multiplied by pi. And if you actually check that, make your calculator operate in radians. So you say sine 0.5 multiplied by pi. That's actually 1, so it's maximum here. And if it's at pi, it's 0. And at 0, it's 0, right? 0 multiplied by pi, 0, sine 0, 0. In radians, anyway. I think in degrees it's the same, actually. But in radians, so that's what you get. So the SPWM is basically you're accessing PWM values from an array that you can either generate using a software or you can actually calculate it in the code. And that's what I'm doing in this particular example. So there's a software, I think it's called TrueSign. TrueSign. Okay. Is it TrueSign or PureSign? Man, I don't know. I have to sort of look for that. Look for that software. And yeah, but it's something sign, right? So you generate it, even if you can actually do it on Google as well and generate an array 200, an array of 200. You state the maximum value of your PWM in your microcontroller, and you just plug that into your interrupt and it works fine. But I actually prefer to do it in the code, because then I can sort of, you know, it's easier to actually do that than to have an entire array and sort of copy the entire array and then paste it. It's a mess. Um, Takes longer, so I prefer to use this particular method. And what it basically entails is using a for loop, and then you initialize the count to 0, and the loop's going to continue until count max, which is 200, the value of 200. And then after each cycle, each iteration, the count value gets increased by 1, and the count is obviously an int, starts at 0. So you equate the count, this particular array, which is maximum 200 array, 200 value array. So the first one, so imagine the count here is 0. So if this is 0, then it's equated to the sign of so basically at first you sort of have to, in the first iteration it's literally going to be 1 divided by the maximum count. So this is going to be 1 divided by 200 multiplied by pi. So for this entire this entire length of time, it's 200, right? It's 200 because we're changing the PWM duty cycle 200 times. So basically at this point, you agree it's going to be 100 in the middle. So 100 there, it's going to be 100 divided by 200 multiplied by pi. And then that's where you get the maximum value. So it's basically that same principle we're using to actually record the values into this array. So you have to sort of take the actual count at the point in time and divide it by the maximum. So in this case, it's going to be, the maximum is 200 as stipulated here based on this equation here. And then you just say that value divided by 200 multiplied by pi. So you do that for all 200. Well, this does that for you and records all that value in there. And then once it records that value, it reinitializes count to 0, and then it starts up the timer, the 50 microsecond timer, timer 1. But it's an timer interrupt, so it interrupts every 50 microseconds as initialized. And so basically this is where you calculate the PWM value. And as you notice, it will give you the actual values between 0 and 1, which is a good thing, because you want to be able to use this on other microcontrollers where you're not quite sure what the 100% duty cycle are on other microcontrollers with different frequencies, etc. So you certainly want the array to be filled with values between 0 and 1 and 1.0. And it's a float array, so it's not just an integer like 0 and 1. Alright, so that's what you get. So that's what this for loop does. It basically just cycles through, just does the sign. It computes the sign for 200 values from 1 to 200, and then it records that in here. And if this value here, if you wanted to change 300 times, you make that 300. Obviously, you have to change the timer interrupt as well to equate to 300 times. Using this formula, and then after that you're basically good to go. It will record everything in here, and obviously you have to change this 300 as well. You have to change this value to 300, this to 300, but this is 200 in this particular example. So now after it's done that and recorded all the duty cycle changes that have to occur in here, which is basically the SPWM, then it will initialize the interrupt. And now in the interrupt is where you actually output that to the MOSFETs. And so first off, what does it do? The polarity, remember the polarity to know which MOSFET pair to turn on first. So if polarity is 0, it's going to turn on MOSFET 1 and MOSFET 2. The first diagonal of these two, MOSFET 1, MOSFET 2. Well, don't look at the Q1, look at the gates. So it says MOS 1 and MOS 2. Alright. So let's just go back there, and then it basically just outputs that. So in the first iteration, count is obviously 0. So it says count 0, PWM poll, and then it equates that value to that, and then count plus plus, and then PWM2 poll is the control minimum, which is literally 0. And I noticed in some PIC microcontrollers, actually 0 is not 0% duty cycle, so you have to say something like 0.005. So 0.5% duty cycle is actually 0, but 0.0% duty cycle, it just makes it 50% duty cycle for some reason. On some microcontrollers it does that. On some DSPICs it does that, and PIC microcontrollers it does that. But this is a simulated perfect environment, so I just left it at 0. It's just something to know if you're going to use a DSPIC. I don't think the STM32 microcontrollers do that. From my experience with them, they do not do that. So you could go 0 with those ones. And so this is what you get. So for the second PWM pair, you want that to be 0, like dead ass 0. So that's why it's 0 there. And then afterwards, obviously, for the actual PWM into the system, so this is OC1RS, and then max duty. The max duty is gonna what's gonna be correlate with this particular microcontroller. So the switching frequency in this case is 20 kilohertz, right? And the max value for that, actually, the according to timer 2, the period value for that is actually 799, right? But one thing I found is you actually don't want to make that there. You don't want to use the maximum. You want to go sort of below that to about 500, 600, all depending. It all depends. But I found 550 in this particular example. I'll show you why in just a minute, but 550 is a good number for the max duty. Even though the theoretical max is 799, 800, but 550 just works just fine as well. Alright, so that's basically that. So you multiply that by this value. Basically, you're scaling it up to be the actual, for the actual microcontroller that you're dealing with. So our max duty here is important, and doing everything on a scale in 0 and 1. So it essentially makes it such that you could use it. The code is reusable in essence, in the form in another microcontroller that's not a PIC, or another microcontroller that's not a PIC 24FJ64GA002, another PIC, for instance. And then after that, you want to check if the count is reached 200, and if it's reached 200, you want to make it 0 again and change the polarity so it goes to the next one. So one let me go back to the image. So one switch pair is responsible for this cycle. The other switch pair is responsible for that. So you wanted to switch to the other one. That's why you sort of have to change the polarity in the code to pole equals to 1. And this is pole equals to 0. And obviously, if pole is not equals to 0, it's equals to 1. So else, the other way. It's literally just the flip side. It's the opposite. Just this time, the PWM2 pole is the one that's getting the SPWM. So this is the SPWM sine array. So it's going to cycle from 0 to 200. Or this particular count value only goes up to 199 because this is an array. So it starts from 0 to 199 for an array of 200 values. Okay, that's also why it says count plus 1 here, right? Because at the 0 point, we want 1 divided by 200 multiplied by pi, not 0 divided by 200. We want 1 divided by 200. So that's why this says count plus 1 here. Alright, and this is timer 1, and this is the exact same. So PWM pole 2 for the second pair, and increase the counter. PWM this time stays at 0, control minimum, which is the minimum PWM 0.0. Keeping in mind that some PIC microcontrollers are weird, and they require you to make it 0.5% duty cycle and not 0% duty cycle to make it operate properly. And then afterwards, OC2RS, you make it, you scale both of them up appropriately based on the max duty, which changes across microcontrollers. This is the only value that should change across microcontrollers, with exception of Texas Instruments, because some Texas Instruments do not have floating points by default. You have to use special library. I actually don't know how that works, but they're like special controllers where you have to, do something else with that particular function. All right, and then afterwards, once it gets to 200, you have to do it again. You have to sort of zero out the count, change the polarity, and so on and so forth. And it basically just does that over and over again till eternity, if the inverter is going to be on till eternity, I guess. Yeah, that's it. That's really it. That's all there is to an inverter. The SPWM aspect, obviously, more advanced inverters, like real world inverters, right? Commercial ones have closed loop control, and then for the closed loop control, you obviously have to include a PI control loop here, and includes AC voltage and current sensors to improve the power factor of the sinusoid on the output. And you have to do all that. I am not touching on any of that. This is just simply how to do it SPWM, because it's literally the main thing for an inverter. If you do not have SPWM, then you basically just have a square wave inverter, which is harmonics laden inverter. Um, and that's basically that. And then yeah, closed loop systems are quite advanced. So alright, so let me just run it again. Do that, and then just copy it, copy that. Alright, so here I basically want to see what's between S1 and S2. So I think it simulates pretty quickly, not take too long, so it's a good thing. And also, alright, so you look at it, basically have SPWM, and you basically have a sinusoid without the filtering. It's SPWM. I'm just zooming there, so it makes a lot more sense. As you can see there, the duty cycle is changing, increasing, 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 and it decreases back down to 0. And essentially, when you design your filter, you're basically just trying to filter this PWM signal out, because it's literally just high frequency stuff, 200 kilohertz. From what I've heard, you sort of have to filter 10 times less than that, less than 2 kilohertz, thereabout. Anyway, let me just try out some inductor values that I tried out. And okay. So for me, this is what I found to work for this. Obviously, this video is not covering filter design. I found a really nice video on YouTube sort of explaining that. I'll link that as well in the description, so you can go check that out. So I think this value here is 4.8 micro. And this was about 400 micro. Alright, let's see what we get. Not perfect sinusoid. Alright, it's done. Right, obviously not the best looking sinusoid I've ever seen, but yeah, I find actually designing the filter for an inverter is easier said than done. So it's quite, quite an interesting endeavor to take on. Yeah. So basically, this is what you get in the end. If your filter was filtered correctly, it should look more like a sinusoid in this. But essentially, that's how you go about doing an SPWM. Like I said, the several ways you could generate the array on online. You generate the array and actually punch the array here, which means you'd probably need. It's probably gonna cover all these lines. There's 200 values in it, or that line, and the scroll here will be so tiny because you have to freaking 200 freaking floating point values. So, but the other way is basically to just calculate the value for the array before you actually start doing the SPWM. Um, and that's what I prefer, and that's why you need a for loop. In this example, you need a for loop, and you basically equate this. You basically run through all 200 values using the sine function. This, of course, is the star of the show, and the pi here is just literally 3.14, and it always calculates. The math library always calculates using radians, not degrees. It always uses radians, so that's why you have to use this pi value here. If not, you'd literally just use 180 degrees here instead of pi, and like literally 180.0, but here you just pi because it calculates everything in radians. And this is the main function to use to just calculate everything, all the duty cycle changes, the SPWM, right? The PWM values for each position, for position 1, 2, 3, all the way up to 200 to this value here, which is the maximum count, right? And then you activate the timer, and then in the timer it switches sides, right? So polarity 1, polarity 0, sorry, and then polarity 1, and that's essentially it. That's how it's done. You just sort of, you just take it out, take it from there. And hardware wise, of course, all the time, hardware is probably 90% of everything because the code pretty much stays the same, but the hardware is so important. As you can see, the inductor and capacitor values are so important, so obviously that's what you should pay most of your attention on. And so that's what this video is essentially trying to show, how you'd go about the routine and the code. If you were to use a PIC or an STM32 Ti, gets a little bit more interesting. Not all of them support floating point um, math functionality like this does. It makes it a lot easier. One actually takes this for granted until you actually find a microcontroller that does not do that naturally. You need several libraries to actually do a math function like that. And yeah, that's about it. If you got any questions with regards to this, then yeah, just ask. And obviously the code will be available as well to play with, to just take a look at if you have to. If you need to modify it, go ahead. That's what it's meant for. It's supposed, so you can modify it and see what you can get out of it. All right, I think that's about it. And all the best in your various applications of this. Cheers. Thanks for watching. Bye.